Hello everybody. Today I'm presenting WINNIE Fuzzing Windows applications with harness synthesis and fast cloning. WINNIE is all about finding bugs in Windows software, and this work comes from Jinho Jung and colleagues at Georgia Tech and Penn State, published at NDSS in 2021. So why is fuzzing used for bugs, firstly? Let's firstly look at how fuzzing applies to security for software. So firstly, when AFL came out in 2013, it democratized vulnerability research. Anybody could download a tool and start fuzzing for bugs. Afterwards, Google had implemented OSS Fuzz in 2016, and the results have been very promising, finding over 15,000 bugs in open source software, libraries, operating system components, command line utilities, all of them found with automated fuzzers. And the idea behind fuzzing is very simple: to generate some inputs for a design or test, monitor for crashes, use code coverage to guide the inputs towards undiscovered regions of the design. And it's based sort of off the genetic algorithm for bug finding, and it works incredibly well for finding hard to hit test cases that a human engineer wouldn't think of naturally. So why is Windows in specific really hard to fuzz compared to some other open source software? Well, firstly, Windows is not an open source software. It's a closed source ecosystem. Everything Microsoft publishes for Windows are commercial applications. You can think of Microsoft Office, PowerPoint, what I'm presenting on right now, other applications on Windows that are running Adobe Reader, WinRAR, Visual Studio. You don't get the source code, so it's not very easy to instrument without having some sort of hook into the code. You can't modify the program to make it more fuzzable, to have the coverage more easily readable by your fuzzer. And you're working with only binaries, and this makes it very difficult to fuzz. The other main problem with Windows is it's practically entirely GUI based, graphical user interface. In order to use it, you need some sort of program like XNView, which is what WINNIE uses. It's an image viewer, and to test it, you need to click through multiple dialog boxes, select files, navigate menus. You can automate it with scripting tools, but the execution speed is significantly slower compared to a command line utility. You can see in our table here we have some programs that WINNIE tested, command line versus GUI, and you can see the ratio, the speed up roughly around 20 up to even 73.6 times percent slowdown just by moving over to a graphical interface compared to the command line, 3 orders of magnitude. And you want to have as many iterations possible to have effective fuzzing. So this makes it very difficult to fuzz Windows to begin with. And lastly, most crucially, Windows does not actually have a fork call. So on Linux systems, AFL, the very popular fuzzer, will set up a fork server and then clone already initialized process for each test case. It's incredibly quick, and it allows the program to be isolated from creating side effects, any memory calls, or regions that would bleed over into other test cases. On Windows, you're stuck calling create process over and over, and you have to reinitialize the entire program from scratch, including the very slow GUI code. So not only is GUI harder to fuzz, but it's not just the clicking that causes it to be harder, but it's also the initialization code. You have to render the window, set up event loops before you can even reach the code that you would want to fuzz and test the core logic of the program. And so this is very devastating for fuzzing. So what is the standard workaround then? It would be harnesses. Harnesses are typically small programs that you'd write that bypass core functions of the designer test. In our case, the GUI. So WINNIE uses harnesses to bypass the GUI nonsense and directly calls the functions that they want to test. So instead of clicking, for example, in our user interaction and you click on File, Open, you can instead just call the parsing function with a file name from the command line. And so before you have a whole GUI stack to get to the image decoder, but afterwards you get a very clean direct path. You can simply call in the command line that calls those GUI functions without actually having to render anything. So in our case, if we use xnview for example, the harness can call functions jpm document start, decompress page, the internal logic that processes the image file, and you don't have to actually click on anything. Now the issue is, well, if you're facing a closed source binary, how do you know what functions to call, what order, what arguments? And this is where manual reverse engineering would come in. And this leads to why harnesses are not made manually because of that reverse engineering. If you're sitting down with the debugger, a hex editor, trying to reverse it, it's trying to answer 4 very difficult questions. Firstly, target discovery or identification. What functions in this really large library actually handle user input? Is it the one that calls refile, the one that takes a parameter, the one that processes a buffer? You have to trace that execution and essentially guess. Next up is the call sequence. What order are the functions going in? Do you need to call an initialization function first? Is there some object that's dependent on this function that you need? Do you need some properties to do this? And so normally the program does this, but you'd have to reconstruct it if you're doing this manually. Third is arguments. What does each function want? Is it some integer? Is it a pointer? Is it a reference to another function? Reverse engineer, you'd have to look at the raw hex types and sort of infer it if you're using a tool like Idra or IDA. It might help you a little bit, but regardless, there's still a lot of work that goes into it. And then lastly is dependencies. So the functions don't actually exist in isolation unless you're using some code like Haskell, where every function is purely typed. So the first function will return something that goes to another function, and then there's error handling if you return something that's non-zero, the program exits. Otherwise, like, it crashes. There's lots of different paths the program can take in that last dependency step of the program. How do the calls actually go to each other? The control data flow step. So if it takes an expert to write out a harness, it'll take days, or even if they're really good, like hours. If that takes that long to make a program, how many programs can you realistically test? And the answer is a handful. It's not very scalable whatsoever. So you might think, well, there's tools that can generate harnesses automatically, and that's exactly what Fudge and Fuzzgen do. But as documented in this table here, they target Linux. So they work only for open source Linux tools. And so the issue is it won't work for closed source Windows binaries, which is what WINNIE aims to address. So instead of taking the approach that Fudge and Fuzzgen use, they have a different approach. So it works directly from the binary using a dynamic analysis of execution traces. So it takes a real execution of the program and it watches the data flow of the program. And so it can reconstruct that behavior in a harness. And so can you approximate the source level understanding without the actual source code? And WINNIE's answer to that is yes, by tracing and analyzing. So at a high level, WINNIE has 2 main pieces that work together to achieve this goal. So there's a harness generator and there's the fork server. The harness generator will take the input program, some sample inputs, just some normal files that would cause the program to work successfully, to exercise functionality you want to test. It'll run the program, it traces everything, and then will synthesize out a C harness that replicates the relevant behavior. Then it can take that harness and test it, but not by restarting the program each time with a Windows create process. Instead, WINNIE actually implements a custom fork server, which implements copy on write process cloning on Windows. So the flow is simple as any other fuzzer. You give it a program, it'll sample it out, analyze it, you get a harness back, Now you can use that harness to fuzz the program and actually find the bugs. So the core of the paper is that harness generation because, well, how does it actually trace out, the harnesses? It seems like black magic almost. Well, firstly, it looks for anything that touches IO calls, input calls. So open file, read file, functions that take pointers to something that contains the file data. And when it finds the function or the library that handles this data, that's going to be your target. So it identifies, firstly, what is your IO target. Then it does something a little bit clever with that. So it's able to recover the call sequence from that target library. So once you have the target library, you can extract out any inter-module call related to that library in the order that it happened. And that sort of becomes your harness skeleton, the order of which your program is executing. And this also works, WINNIE does work for multi-threaded programs, so it'll filter out by the thread ID, so you only get relevant calls. And by cutting it per thread, you can actually significantly reduce the irrelevant calls from other threads and really refine the skeleton of the harness. And the third step they take is, the argument recovery. So how do you know if a value is a pointer or integer? It'll run it twice with address space layout randomization enabled. That is a modern security feature in Windows. And since the pointers will change between runs due to randomization and constants don't, if the same call site gets two different values, but they're both valid, it's probably a pointer. Otherwise, it'll be a constant. It'll also trace multi-level pointers recursively to also resolve those out. And then lastly is your control flow and data flow reconstruction. So WINNIE will connect the dots between all the calls. So if a return value from one call uses a argument in another, it becomes a variable. And it'll check return value and exit on failure. WINNIE will add in an if statement that'll handle if it exits on failure or if it returns successful. And so the result then is a C program that mimics the original behavior without the GUI and just simply the file handling code and what it actually does to your input. So in practice, what does this look like? So I'll quickly go over what they showcase in the paper with the XN view example. So there was 101 lines of code for the parser, and out of that, only 4 were incorrect. So the call sequence, firstly, was very correct. It started with document start, and then it gets the page property twice, so line 15 and line 17, and it uses different constants for that. So that's exactly what the real program would do. And the constants, the hex constants A and D, are magic values from the trace, and WINNIE preserved them because those weren't pointers, they were just constants. And so afterwards, it detects the relationship between the file handle, so it'll pass that to library, and we can see that it'll do decompress page, it'll have the callback function, and then lastly it'll do document end. And you can see that for all the calls, like document start, get page property, it has that same handle for all of them, so the F0, A0. Obviously the name isn't resolved because it's an automated tool, but the reference to the actual file is preserved across all of those. That's what the calc call is done internally. And the lines that needed manual fixing were actually the code pointers, and those types, the type of the pointer actually just needed a bit of adjustment. So 97% correct out of the box from a closed source binary, so quite impressive for an automated tool. Now jumping back to the fork issue is the second big issue of trying to fuzz stuff. So when he handled the automated harness generation already, but if it's not fast enough to actually fuzz the program on Windows, then it's quite pointless on actually making the harness. You've just converted a GUI app to a CLI app at this point. That's all they've done. So why is Linux fast? Because of fork. So on Linux, it uses copy on write. So you start the program once, it'll initialize, and then you can set up a fork server. Each test case, it clones the already initialized process copy on write, so it only copies it when something changes from the original program. Each child gets a clean slate, and the crashes don't affect the parent. On Windows, there is the issue of create process. Every time you copy it, create process is essentially what the fork is on Windows, but every single test case starts from scratch. You have to load in the executable, load all the libraries, run the initialization code, render in your windows, and then reach your target function. And you can't actually create a copy on write replica, basically. You have to create a completely new process every single time. That's much, much slower. There is a hack that's called persistence mode, and instead of restarting the process, you loop inside the same process calling the target function repeatedly. And this is really fast. The issue is that this assumes that your target function is a pure function, so it has no side effects. It doesn't affect memory outside of what's contained locally in that function. In reality, the Windows functions will leak memory, they'll leak file handles, they modify global variables, they can call exit on air. Think about what happens if you leak something like 1 kilobyte for 100,000 iterations. Well, your computer is going to hit the memory limit and crash. Or what happens when the global flag gets set on the first run and it crashes your fuzzer on the second one? It's not fuzzable very well. So persistence mode is very difficult to work with non-pure functions, especially with the Windows code when there's a lot of code out there that is closed source and has bugs like memory leaks and such. Now, WINNIE says that Windows actually does have fork capability. It's just undocumented and broken by default. So the kernel does support creating a child process that shares the parent's address space with copy on write. And there's a special call for this called ntcreate user process. But the catch is the client server runtime subsystem, or the CSRSS, as I have written on the slide here. Every process needs to be registered to it with Windows 32 APIs, which is basically everything. Everything's a process on Windows, right? So when you fork a process normally, the child inherits the CSRSS connection state, but the state isn't valid yet for that new process. And in the first time the child calls an API, it'll crash unless you correctly make a new CRSS. So WINNIE attempts to get around this with this 4-step process. So it'll first create the new process with those flags that I talked about, the ntcreate user process, and it'll create a suspended child. So the child is not actually running, but it has a copy of the parent's address space. Next, the parent calls the CRSS and tells them about the new process. So it's alerting that here's my child process. Then step 3 is that the child becomes unsuspended. And then the 4th step, the child will zero out the global variables in the CSRSS inherited from the parent, and it'll continue to run then. And so the result from that is the child can run like nothing ever happened. And so the reason this works is you're essentially wiping at the memory of Windows's process manager. So the child process is technically like a zombie process, and it'll continue to run from the fork as if it was actually initialized by some other process. The parent didn't actually clone it. And so the execution of WINNIE, the way they do it, allows 310 executions per second compared to 31, which is plain create process. So 10x speed up essentially over the native way of doing it. Now on to whether they actually did anything with this, and the answer is yes. WINNIE does find real bugs. So they list out 61 bugs in the paper across 32 different programs, and so there's 19 different bug types that they identify. They have overflows, type confusions, double freeze, dereferences, uninitialized memory use, things like that. And a bit notable is they have a couple of actually like Microsoft utilities. So one is makecab.exe, has a double free. The Korean Microsoft Office program, Hancom Office, had 6 bugs in its TIFF parser. And even really popular programs like VLC Player and ALZzip had identified bugs in their Windows specific code. So these are all in the latest version of the paper, 2019, as a reminder. And these are very large programs. VLC, I'm sure most of you have heard of that. FFmpeg, Visual Studio, Microsoft Windows itself. They've proven that they can find bugs in very commonly used new software. Now, it's not all sunshine and rainbows. WINNIE does have some very important limitations. So firstly, harness-based coverage means that they can only test what's actually in their traces, their samples. If the samples don't test certain features in the programs, it won't be able to generate harnesses that can test those features. So if you don't have enough samples, well, your results won't be great. You'll only be hitting that small subset of features in the program. Secondly, tightly coupled programs are very difficult. So Adobe Reader, for example, is a wrapper essentially around a giant DLL file. There's lots of cross-module calls, callbacks from the library to the main executable, complex interactions between those two. And WINNIE can't handle this very well. There's so many components and dependencies within the program that it's extremely difficult for it to fuzz. But if the program is simpler, WINNIE can handle that. More complex things, it becomes much more difficult to actually create harnesses for. Next is false positives. Now, if WINNIE generates an incorrect harness, you would crash in ways that the real program would never crash in. And this is a big issue with triaging, is whether you have to validate if it's a real bug or the bug in the harness. And you don't want it to be a bug in the harness because it's not real. And the paper argued that 95% of harnesses need minimal fixes, which is still 95% of the harnesses need fixes. So take it with a grain of salt. But ideally, you'd want harnesses that work out of the box and they don't cause issues that the real program would never face. And then lastly is structures and callbacks. If you're trying to reconstruct an arbitrary struct layout from memory trace, that's very difficult. Same with callback functions. If you're calling like an inline function that does something very specific in assembly, WINNIE is not able to generate code from that. If the code that you're trying to fuzz optimized to some decent level, or it has very esoteric programmers behind the project, it's going to be very difficult. And the current solution to that really is just to label it out to the person running the fuzzer and copy the decompiled code from another tool. You have to do some reverse engineering for that. So some questions to think about is, firstly, WINNIE focuses mostly on file processing libraries. How could it be extended to maybe fuzz network services? Could you direct like socket traffic to the fuzzer? Would you handle connection state, multi-step protocols, network timeouts? It could be done to fuzz possibly Windows network protocols. Secondly, what's the trade-off between persistence versus fork? Persistence is much faster when it actually works, but fork is much more reliable. If you were building a continuous fuzzing service for Windows applications, what would you use? Could you try using both and maybe fall back to fork when persistence fails? How would you detect when persistence mode is failing? And then lastly, the fork implementation. So Windows does have the undocumented quotation marks, the undocumented implementation of it, but what would them actually making a fork API entail? Would it help fuzzing, or would it be a severe like security drawback? Could attackers possibly use it to make zombie viruses that run in the background of your computer. Food for thought. So that's WINNIE. I hope you're curious to read the paper for the fine details that I glossed over or didn't even cover for you to uncover. The valuation methodology, the actual implementation specifics, case studies, or the specifics on the bugs found. I've linked the paper and the code on the screen, and I hope you guys enjoyed. Thank you.